So here we go. Okay. Yesterday Tuesday in lab, you guys came up with the density of two objects. Okay. There's your proper. I don't know which color y'all use, but here's a block. And how you did that was just to get the mass and the volume of each of them and do a division. So density is always what we say the ratio of mass divided by volume. Mass to volume. All right. And then don't forget, I mentioned on Tuesday that we use that symbol rho, the Greek letter rho, it's like a P. Okay, that's the symbol that we use for density, not D. Okay. So here's one thing about it. Since density, the way you get density is you take mass divided by volume. You guys buy this, that the volume will change with temperature. Now, like for instance, and I think I've got a slide to kind of show you if we deal with water. Liquid water. Now, I'm not saying when liquid transitions from a liquid to a solid, but it's a liquid, and say you go from 20 degrees Celsius to 10 degrees Celsius. Liquid water, yeah, it freezes at 0. 20 degrees Celsius to 10 degrees Celsius. It will shrink. Liquid water will shrink. Okay, and it will shrink then all the way, actually, it will shrink all the way to about, I think it's 4 degrees. And then start to get ready because it's going to transition from a liquid to a solid and it will start to kind of fluff out. But my point here is if you're taking liquid water, you take a certain amount you get the mass, and it's going to stay the same throughout those temperatures of 20 to wherever. The mass is going to stay the same unless you're dealing with something weird. But its volume will change. Okay, so you kind of have, it's going to change. Our glassware, we talked about different types of glassware to get different kind of precisions of, small amounts of liquid. And like the pipette one that has kind of the little thing that you're never supposed to use it like a straw, you're supposed to use a pipette bowl. Well, on the side there, it says, I think it says to deliver, TD, at 20 degrees Celsius. So they're like, dude, it's only good for 20 degrees Celsius. Around that. So liquids actually expand and contract with temperatures. Solids, and actually this could be something relative to what the terrible freeze that we just recently undergone. Solids actually too will change volume with temperature, but not as much. A good example of that is why you're making a sidewalk and you segment your sidewalk, right? Because what happens in the summertime? It expands, exactly. That's an example of the volume of a solid increasing with temperature. And when it gets cold, it will contract. But, oh my gosh, there was these, and my mom even said, she had all these weird noises under her trailer with this cold. Was it Wednesday, Tuesday, Wednesday, and it had to do with like the crazy temperature drops, and I think it was water.
I think they called it frost quakes.
Frost quakes.
Yeah.
Yeah, she was kind of worried. But gases, oh my gosh, they are terribly persnickety when it comes to temperature. You figure if I have gases in this room about 20 degrees Celsius. If I were to snag a particular volume of gases and go ahead and cool it down, keep the same pressure, it's going to actually, as I cool it down, those gas particles can slow down at the same pressure, they're going to actually have a smaller volume. So gases will get smaller, the volume and temperature, so the same pressure. The gases are the worst. All right. So in this class, we've been talking about properties. Property is just a characteristic about something. A way to describe it. We talked about physical versus chemical properties. We talked about intensive versus extensive properties. We said physical properties are something you can gauge from matter without having to do any sort of chemical reaction. So density, mass, we measure the mass, measure the volume, nothing destructive there, right? So it's a physical property. What does intensive mean?
It depends on
Independent of amount. Very good. So this water has a density. Water's awesome. I'll kind of throw it up here. You're like, really? How could that be? Water's so important to us, but the density of water, of course, in its liquid state. So you're talking kind of runs about 1.00 grams per milliliter. I just think that is such a cool sort of deal. You know what I'm saying? Oh, really? Yeah. It runs about 1.00 grams per milliliter. My point was going to be that if I have this amount of water, the density is going to be 1.00 grams per milliliter at a particular kind of ballpark room temperature. Or if I have a whole bathtub full, or like a little tiny beaker, it's independent of amount at that temperature. So yesterday in you know what I mean, Tuesday this week, you guys came up with a density of two objects. The masses were both grams, but your volumes were different. Okay, the volume of this guy was centimeter cubed. The volume of this guy was milliliters. Okay, so you came up with, actually, this density was grams per centimeter cubed. This density was grams per milliliter. It's awesome. One of the things about working problems in physical science, including chemistry, is you just gotta keep your wits about you and keep the units with when you work the problem, and then slap the units on the end. Okay. This down here, so this is grams per milliliter. This is also grams per milliliter. This middle one right here is going to be nice. So this will make more sense to you maybe later today and actually into next week. This is easier to work problems when you have it like units in the numerator, we call it top, and units in the denominator, in the bottom. Okay, this one is kind of weird. Okay, anything raised to the negative power is that item means it's in the denominator. So grams times milliliters to the negative first means this. Okay, these two mean the same thing. And so grams to centimeters cubed raised to the negative first is the same thing as this. Cool. So what did you guys do to calculate density? Well, you found the masses, you found the volumes, and the ratio means a division. You took a ratio or you divided them out. Okay. Units of liquids and solids are usually grams per milliliter or grams per centimeter cubed. Units of densities of gases are usually, instead of the volume in milliliters, centimeters cubed, usually gases are liters. So this is going to be like, we did that, right? This is what you guys did with your block. You came up with the length, the width, and the height, okay? And then you multiplied them all together. But now just eyeballing this, how many sig figs, let me get my pen, or you get your fingers ready, how many sig figs are in the length?
3.
And 3. How many sig figs in the width?
3.
And we're also 3. How many sig figs in height? 2. So regardless of what our calculator spits back, what are we supposed to round it to? 2. Just 2. That's it. And then the mass was 13.94 grams. Okay, so here we go. Now one of the things I'll be looking for, and now when I grade your homework, sometimes I don't look at it very closely, like real closely. But one thing I need to tell myself I need to be looking for is when you work a problem, you have to carry the units around. Carry the units. There are no naked numbers. As you show all of your work, and all of your numbers need to have units. So there you go. So you guys told me 2 sig figs. Yep. So the beauty of making sure you have the units in the numbers as you work the quantities, making sure you have the units with the numbers, the quantities that you're working with in your problem, you can take the units and the units will show up in your answer. So you can see why we have units of centimeters and centimeters and centimeters all multiplied. So centimeters times centimeters times centimeters. So that's the same thing as centimeters raised to the third power centimeters. That's it. Sometimes I guess I should say don't make it harder than it is, right? So rho or density, the density of this alloy, this metal alloy, is simply the mass that was given on the previous slide, 13.94 grams, divided by 1.8 centimeters cubed. Now, is this the one? I have my thing open. Yes, I did. I think it is. This is our first example. Now, if you have your calculator, you can do this too. I'm going to take 13.94 divided by 1.8. Okay, I get, it's like a magic trick. Okay, I get 7.74. How many sig figs am I allowed? 2. So from my calculator, I would go with 7.7. And what would the units be?
Grams per centimeter.
Yep, grams per centimeter cubed, exactly. Okay. Now, I do make mistakes in my answer keys, not on purpose, although I think it's kind of funny when you guys find my mistakes. But this is not a mistake. The way somebody would get this answer, 7.9, is to use an unrounded value from your volume. Okay? If I take 13.94 divided by quantity 2.21 times 1.05 times 0.76, okay, I get 7.90437. 2 sig and 7.9. So I'm here to tell you this is my problem, not yours. The difference between these two numbers is this number I used an unrounded value here, and this number I used the rounded value. So they're both awesome. They're both great. Any questions about that? So some would say, and rightfully so, if you're kind of tracking with what I'm saying. So 7.7 is great. The advantage of using the unrounded value here and getting 7.9 is it's a little more with it. The disadvantage to using an unrounded value down here as you go ahead and take the mass divided by the volume is you forget how you're supposed to round it. So, let me know if you have any questions. All right, but that's why you might get slightly different answers. All right. This is like the whole naked number, the whole no naked number, excuse me. You should always have units next to your measured quantities. The dimensional consistency just means dimensions means units, so make sure your units come out right. There are sometimes, and I still get, not lots of people, I've taught a few people here and there, right, but over 15, 16 years. But this idea of leading up to the factor label method of working problems, making sure your units come out, is one that students come back and say, I'm so glad I learned that. So, dimensional consistency is actually a way of working physics problems. Making sure you have no idea how to work it, but you know what the units need to be. You just start plugging in numbers, make sure your units come out right. Okay, so density of water. I kind of mentioned the whole idea that liquid water is going to be water when it's in its liquid state. If we cool it from 20 to 10, its volume is going to get less. Now, as its volume gets less, actually, can you see where the density is going to increase? It's more compact. In other words, if its volume gets less, this number gets less, and I'm dividing by a smaller number, so my density is going to increase. Density increases, density increases, density increases about 4 degrees. It starts to kind of rearrange, gets ready to isolify, to solidify, form those awesome little ice crystals. All right, so I mentioned this before, and actually if you want to put a little arrow there, I know for my general chemistry students, I don't know about introduction to general chemistry, but you should really know that. You should memorize that. Okay, so this is the whole, here's my 4 degrees. And here, actually, this is getting colder from right back to left again. So do you see where the density is increasing, getting colder, getting more and more dense, getting more and more dense? I said about 4 degrees, it starts to get ready to solidify. And so about 4 degrees, as I'm getting colder and colder, actually the density is decreasing, which means it's fluffing out a little bit. But check this out, right at 0 degrees Celsius, where it transitions, look at the jump there. Woo! So the density of water at 0 degrees is fluffier than 4 degrees, and then from 0 to like -1, it fluffs out. Then what happens as it's a solid? What's the trend as it gets colder? What happens to the density? Density increases again, so we're back to like that's a normal solid. Okay. So these two objects, so which is most dense between those three things? The rock, the styrofoam, and the water? The rock. Yep. What's the least dense? Styrofoam. Yep. So here, sometimes I've had students we kind of talked about, this is the density of 1. Okay. How many people think that this will float? Now, if it floats means it's less dense than water. How do you think it will float? Ah, okay. How about this? How many people think this will float? How many people think it will sink? So, yep, the most dense supper, the least dense block in between water. Okay, so these are densities of some substances. It doesn't say at the top there, it really should, but temperatures, if it doesn't say, it's about 20 degrees Celsius, which is a little chilly, but 20 degrees Celsius must be kind of what labs are around. This is density of some substances. Platinum, woo, okay. Lead, very dense. So the red note there is actually more of a note to me than a note to you. What did you guys say? Assignment 29516. Oh, you guys have the 6th edition, so you guys should change that. Don't you think? 299 to 100.
Process out and put 299.
Yep. And that should match up with my answer keys. Okay. Well, the other thing that we did was the egg, right? That's what we're going to talk about now. I think my husband thought that was pretty funny that I did not get my eggs hard boiled, but anyway. So what you guys did with the egg is you had 3 components. It was a hard boiled egg is you guys told me heterogeneous mixture. You divided it out into components. You had mass of the total egg, and you had some mass of the individual components, and you did a division to come up with the weight percent of each component. This is actually then kind of unpacking. This is what I say unpacking. If you're given the mass percent of anything, percent means parts per 100, so we can unpack percent, weight percent, mass percent. And so that means that that is so many grams of your component out of 100 grams of mixture. So for instance, I can't remember, but if you guys came up with, 17.5% yolk, okay, what that means, I can unpack that, and that means 17.5 grams of yolk in 100 grams of the mixture, which is the total egg. Okay, so that's what I mean by unpack. So there are times when you're going to want to take a percent and to say what it means. Now when I go like this, hopefully you guys are with me, numerator, denominator, divisor. Right. But we didn't have 100 grams of an egg to get 17.5 grams of yolk. We actually had kind of a miscellaneous mass of our total egg, but we had and we had a known mass of the yolk that came from that total egg. So this is what you guys did to get your weight percents. mass of the component divided by the total mass of the mixture, in the case of the egg, times 100% to get parts per 100. That's what you did. Now, there is something related to percents, okay? Mass percents, weight percents, and it's called mass fraction. Okay, mass fraction or weight fraction, they're totally related to, like, well, if you get one, you basically got the other. The difference is, instead of grams of component per 100 grams of mixture, it is grams of component per 1 gram of mixture. I don't know if you guys, I played with my slides this morning, so I just added this morning. So if you don't have this, you can add it. So by definition, and I'll pick on this example over here. Do you guys buy this? And I kind of hesitate to do this because we don't do a lot of kind of like the ratioing down. But for this same example, so this is the weight or the mass percent. Do you guys buy this? That for the same situation, I could just move the decimal place over 2 places. So in 1 gram of mixture, how much yolk do I have? It's the same. Instead of it's not 100, it's 1. So how much? Is that what you can say, Gabe, too? Yeah, very good, guys. 0.175 grams, exactly. Okay, so they differ by a factor of 100. So mass fraction looks very similar. Calculating mass fraction, I added this just today. So calculating mass fraction, all you do is you don't do the times 100. That's it. I'll make it harder than it is. Okay. All right. So let's do an example. Okay. So whether I need to or not, I make a drawing, and my drawings aren't as pretty as some of you guys' drawings. But a drawing for a problem does 2 things. One, it helps organize the information, and the other thing is it helps you stall. It helps you like get a sense for what the problem is. Now this one you're like, I got it, but draw a picture. So here's a picture for this one. It tells a story. 5.42 grams of sucrose. So I do a lot of beakers, and if you read it a few times, I'm going to take 5.42 grams of sucrose, and I'm going to add it to 28.72 grams of water. And I'm going to mix it all together so it's homogeneous, so there must be no sludge at the bottom. So we're supposed to come up with mass fraction and mass percent. You could do this a few different ways. You come up with mass percent and then kind of backtrack to mass fraction. I think the way my slides do, sometimes there's more than one way to skin a cat, which actually came from skin a cat. There's more than one way to skin a cat. Okay. So let's go with mass fraction first. So mass fraction simply is the mass of the component of interest, which would be the sucrose, divided by the total mass. So how am I going to get the total mass? Mass of mixture. And this is why if there's a picture, you're like, oh. And then you guys are thinking this. All I got to do is add these 2 together, and that will give my total mass. That's going to go on the bottom. Yep. And I probably would do this stepwise, because if we're adding, then we have to round according to decimals. And if we're dividing, we have to round to yeah. So the total mass of the solution, remember solution is the solute plus the solvent. So solution is the little bit and the big bit. So I probably would do that this way and round it and then do one last division at the end. So we take the mass of the sugar, 5.42 grams, plus the mass of the water, 28.72 grams. And so how are we gonna have to round this?
2 decimal places.
I agree, 2 decimal places. And that's a good example. So the thing that's gonna go in the denominator here in a minute is the 34.14 grams. That's a good point where if we were multiplying, we round according to sig figs, you tell me 3 sig figs, but we're not, we're adding, so we'll go with decimals, and it's 2 decimals. All right, so now what we're gonna do. So ready to plug in this. This will go in the bottom, what goes in the top? Yep. Mass fraction simply is the division of 5.42 divided by 34.14. And I messed up there. You need to make sure there's no naked numbers, so make sure the units. So of course it's 5.42 grams divided by 34.14 grams. And do you see where if I was going not for fraction, if I was going percent, I would multiply by 100 or 100%. Okay, so let me see some fingers here. How many sig figs?
3.
3. Very good. All right. That's it. 0.159 would be the mass fraction. And people are like, mass fraction, what in the heck is that? Well, it's a hop, jump, and skip away from mass percent. Okay. Mass fraction, mass percent. That exactly.
Doesn't that need grams at the end of it?
No, that's a good question. Actually, and we're going to talk about units that cancel. In this case, we're going to let the grams cancel, so it actually gets unitless. No units. Good question. And I'm not real thrilled about, I think I added to this too. Oh yeah, mass fraction is unitless. So if somebody tells you the mass fraction of sucrose is 0.159, you're like, really? How am I supposed to use that to my advantage? I call it unpacking, but if somebody gives you that number, 0.159 is your mass fraction, this is what you need to think of it. This is how you need to unpack it in your mind or use it in a problem. 0.159 means that there's 0.159 of the component, in this case sucrose, in 1 gram of the mixture. In this case, the mixture is a solution. All right. So I added to this one. So mass percent is equal to mass fraction times 100%. I just added that today. Because it makes sense to me if you compare how you get to mass fraction, mass percent, they differ by factor.
Go back to that last page for a second.
I can't. It's funny, the years I've been teaching this, I'm like, I should do that. So I'm like, yeah. So do you guys buy this, that 0.159 becomes 15.9? Okay. There you go. So again, unpack, I use the word unpack a lot. So, and you're going to have some problems when you're going to be using percent in your problem. And I'll just warn you ahead of time, I should never see like 15.9% just like that, 15.9%. I should never see that in a problem. Instead, to work the problem off, this will make hopefully more sense to you as we do some more, see how this works. But this is what I'll be looking for in the problem. Unpack. So it means 15.9 grams of the component, in this case sucrose, per 100 grams of the mixture, in this case a solution. All right. So do you guys have this one? Okay. So I actually want to, if you could say homework right there, that'd be great. So that one's going to be due also. And then, of course, we have homework here. The chemistry starter weekend. Okay. So I want to go on to the next part for a few slides. Oh, and the other reason, it's not just because I'm saving time, but the other reason for you guys to do that extra homework with the salt, the sodium chloride, is to give you more practice at like what you're going to see on the test. Okay? It's only because I can. All right. So this class keeps kind of building on itself. So one thing I told you is going to be here throughout the class is that idea of rounding. If you're adding and subtracting, you round according to decimals. If you're multiplying and dividing, you round according to significant figures. That's it. That's here. This is another kind of keystone in kind of the way the class goes too. When we're dealing with kind of the number part of chemistry, we're always going to use what's called the factor label method of working problems. And probably this was what I tried to say, not very articulately, this morning earlier, that people have said, I'm so glad you showed me the factor label method of working problems. It actually can help you with anything that you do. So, one of the things that's important in this method of working problems is this idea of having equivalency statements. So when I hold my hands out like that, that just means that I have two quantities in both hands, and between my two quantities is an equal sign. That's my equality statement. I told you need to memorize this one. Okay, 1 inch is exactly equal to 2.54 centimeters by definition. Do you have to memorize this one? No. This one? But for those other two quantities, and this will, as we do some more problems, this will hopefully sink in. When somebody says 1 gallon is equal to approximately 3.785 liters, the word approximate means that there's some uncertainty in that relationship. But I want you to think of it this way. Exactly 1 gallon is equal to approximately 3.785 liters. So when we use that, and we're going to be using that in more problems, I'll remind you of this, but we're going with the 1 in the 1 gallon, no uncertainty. And I mentioned this when we were talking about significant figures. If there's no uncertainty in a quantity, then you don't have to count it when you're trying to round. There's no uncertainty in that one. There's no uncertainty in this one. Okay? All right. Do you have to memorize this one? Yep. Within the metric system, 1 milliliter is exactly like one cute little centimeter cube, cubic centimeter. Yep. That's the volume thing within the metric system. Yep. Okay. So you can kind of think of the factor label method approach to working problems is they don't go in this order, but they're things to remember as you're working problems. One is that no naked numbers. Always have units there. Okay? Like when I grade your homework, I'll probably hopefully be looking for that. Always units. And the other thing, and this will make more sense here in a minute, but we're going to take an equivalency statement. Okay, I have an equal sign there. Okay? And we're actually going to make what's called a conversion factor or a unit factor out of these two quantities. And check this out. So you can take this, I'm going to put my left one on the top. Actually, there's a divisor. I just made a ratio. That's going to be my conversion factor. I'll go back to my equals and put this one on the bottom. Okay. Those are two different conversion factors we got from a single equivalency statement. I'll show you what that looks like. You're going to do that, and then you're going to go ahead and set up your problem. There might be multiple terms kind of multiplied by each other, and you're going to go ahead and make sure that the units cancel. Now, units will cancel if you have a unit in the numerator anywhere in your terms, and that same unit in the denominator anywhere in your terms, they get canceled. It's so exciting to get canceled. Okay? So that's kind of how this whole thing works. You're going to multiply the measured quantity, the thing you start with, and your conversion factor or factors so that your units cancel that need to, and you're left with units that you want to be left with. So here's one for you. What do you think? 2.5 feet, how many inches? 30. Seems reasonable because 2 times 12 is 24. A half is 6. 24 plus 6 is up to 30. Totally right. So here's the deal before we move on. You're right. We're going to work this again using this method I've been talking about. But do you guys see the 30 inches? And get your fingers ready because I want you to tell me if you see if we're all on the same track here. 30 inches. That's the way it's written. How many sig figs are there? Oh, yes. I see 2. There are 2 sig figs. Why? Because I put a decimal. Yep. I cared enough. The uncertainty must begin there. And yes, very good. So let's see. Let's see how we can do this the long way. Sometimes you're like, Mrs. Snipes, that's so easy. You just say it's 30 inches and 2.5 feet. I know. But here we go. So what you have to do is come up with, and sometimes there's more than one, but come up with an equivalency statement that will get you from where you are to where you want to be. In this case, we are at feet and we want to get to inches. Feet to inches, feet to inches. Oh yeah, I got this. So within the English system, 1 foot is exactly equal to 12 inches. That's how we're going to accomplish that. We're going to use that equivalency statement. So with any equivalency statement, I mentioned this before, you can actually get 2 conversion factors. But let's see how that works. One of the things we know is we can divide both sides, both quantities by the same thing, okay? And that's fair, hey, in math. I'm not a math teacher. Although I was talking to our Academic Achievement Center up here by kind of our fleeting bookstore. The Academic Achievement Center has both writing and math. So they have a really awesome tutor in there. He's there from 9 to 1, I want to say. So drop in if you have math questions about anything in this class. So we can divide both sides, for instance, by 1 foot. Like, why would you do that? Well, I'll just bear with me. Divide both sides by 1 foot. And what's 1 foot divided by 1 foot?
1.
It is 1. What happens if you have a series of numbers and you throw in a times 1?
Same thing.
It's the same thing. So basically, we can take this ratio, plug it into whatever multiplied by, and just like multiply by 1. Okay? So, very good. Well, we could go ahead, revisit our equivalency statement, and divide by 12 inches. Of course, you tell me 12 inches by 12 inches is 1. Okay? So we have 2 quantities. Oops. Well, I guess it's the same thing. We have 2 quantities, okay, that are equal to 1 related to feet and inches. So here we go. Let's revisit the problem. We wanted 2.5 feet to convert to inches. My next thing is I always start with the thing you're trying to convert. So that's going to be 2.5 feet. And my notes don't do this, but I'm going to go ahead and do it. I usually emphasize that units of feet are in the numerator. So I would put 2 feet over 1. You guys see where 2 feet over 1 is the same thing as 2 feet. And then if you flip back to your previous page, we are going to pick one of those 2 ratios, one of those 2 conversion factors. The one that gets us down the road is the one that's going to allow my feet to cancel. So is it going to be the first? How many people think it's going to be the first one? How many people think it's going to be the second one? I lost track of what the first and second one. Okay, here are our options. Okay, so I want feet to cancel. I could use this one, or I could use this one. That's easier. I want feet, I want my feet to cancel. How many people think I'm going to use the first one? How many people are going to do the second one? It's the first one. And the reason is because if I use that ratio, like I said, you kind of look across the board, all the kind of, I call it a common divisor. Basically, I have a common divisor. If I have units in the top and units in the bottom, they're going to cancel out. And then in our calculators, by golly, 2.5 times 12, you can check, you're getting 30. But like you guys, thank goodness, you guys did great and caught that I don't want just any 30. Why do I need to put a decimal there?
You need to have 2 significant.
Yep, because I need to have 2 significant figures. What you guys have been doing with your problems and in the lab is, you said, and I told you, well, first off, this brings no, let's see, I'll do it this way. I think I usually do this way. No uncertainty. No uncertainty. Okay? So the only uncertainty is brought by the 2.5. And the reason we need 2 significant figures is I have 2 significant figures there. So by golly, I have to kind of clean up what my calculator doesn't know about. Well, let's double check. What would happen if I went with the second one? What would my units be? Well, I got feet squared per inches. Does that make sense? So the units that we're multiplying, the units don't go away. The only way the units go away is if they can cancel. And that's exactly what we did there. So here, being honest, I have feet times feet, which is feet raised to second power in the top in the numerator, that inches in the denominator. And the other thing is, 2.5 divided by 12 is not 30. Okay. I think that's a good place to leave it. You've got one under our belt. Many more to come. Looking ahead at what we need to cover before you have your unit exam, which is going to be a week from Tuesday, your unit 1 exam. We just have some factor labels, some more factor labels, a little bit about temperature and heat, or temperature, yeah, and thermometry. So I think we'll go ahead and end it. That's a good place. I do answer email questions on the weekends, not at weird times of the day or night, but if you have anything, let me know.
I had trouble with the last forms. It's I got the rough out on but
Oh,
I think we had to do right, but if I did bad, I was like, wait a minute.
sure. And did you know, like I said, was you were actually
Yeah, I went over the notes and stuff. I didn't check the answers because I thought I'd do it myself first. But and then I just got tired of it.
If it's the ones I'm thinking about, if it's the ones I'm thinking about, it's probably going to be like, I'm not going to sweat it too much because usually all that we do is okay. Yeah.
Okay. And I'm not worried about the grade itself. I just want to actually know how to do it if I did it wrong. Because I don't know.
Okay. Very good. Sounds good. Let's start. Yeah.
I'm not going to be able to be here Monday.
What?
I'm going to Culver Stockton actually.
Whoa! Excellent.
And be doing classes there all day.
Okay. Okay. So can you get notes from Archie?
Yeah.
And then can you send along the homework? And I record the lectures, so I don't know. I can put a Twitter feed in my syllabus. Yeah. Well, safe travels.
Yeah. Hopefully the weather is going to supposed to be nice and warm this weekend.
Yeah. We'll take
Should
it.
be better.
Yeah. That's terrible. That cold. Oh my gosh.
I heard 50 degrees by this weekend.
Nice. See you later.
Good afternoon.
Feel like such a nerd.
Why?
My dad's so heavy. Walking through the halls. My shirt. Seems clean in here.
Huh?
Seems clean. It's just the light. Oh, nice.
clean grab. Yeah, dog. Mm. What did you ever do with the pumpkins that we got?
It was out there for a long time.
Mine are like still sitting in my house, like orange. What am I gonna do with these?
Wait, they're like.
Yeah, they turned super orange like a month ago or more. They just been sitting here. I was gonna put one outside there froze and see what happens.
Is inside?
Yeah.
Oh. Mine like deteriorated.
Really?
Yeah, I put it on like the corner of my garage, and the water drips down onto it.
Oh.
So it fell apart. But it turned orange like pretty soon after it happened.
Yeah. I don't know what to do with it.
What's cool? It's like
I should have put one out when it was like super cold, because it would have like all the water molecules would have expanded, probably like started to crack or something. It would look cool or something. But I didn't do that. So yeah. It's what it is, dude. So when do you want to try to finish those like grabs? Like Monday or something?
yeah. I mean today.
Wait, what are you leaving today?
Wait, do you have one for today?
Yeah, it's two.
I'm gonna just finish that. I think on Wednesday.
Okay.
Yeah, so we have time.
Wait, you have the exam next week?
No, she said 2 weeks.
Oh.
Would you like?
Huh? What?
Would you like me?
No, it's bad. Dude, pretend it's your tongue though. It's like a dog. Yeah.
Are we here early? What's going on? Yes, we are.
Say what now? Dude, for some reason, the lab report, the results of the discussion about calculations like confusing me. Because I thought the greater the temperature change, then that would mean it's less volatile because it would require more energy. But that's not what happened, because the greater the temperature change, the more evaporation happens.
I actually didn't know that there was like 2 definitions for volatility. I had to look it up. Turns out they're all.
Yeah, because I thought it was for something else. Well, isn't it like
Like if
aggressive or
someone-
something?
If someone is volatile, I thought it means that like it changed, like be one thing and be like a different thing. Which that is what it means. But there's also volatility, which is like a substance, how quickly a substance evaporates. Are they here?
I don't know.
Sorry.
Yeah, me too.
It's not like walking down this way.
I don't know.
She's like really close and then she disappeared. Where'd she go?
Coaching you.
Yeah.
love walking the street.
I had this really scary dream last night.
Got kidnapped. Dang, that's scary.
It's happened twice.
My abuelito got kidnapped like